then we only had done that little corner. We would have missed like whatever fraction of our notes. So, I love how the book starts, because every section they start with a problem. Then they say at the end of this section of description, we'll solve it. So here's the problem that the book starts off with. Cold Region State College has several cases of frostbite, poor kids, right? So they're worried about the kids. So they have these buildings all connected, and these are all the walkways. Again, like I said before, the bad video that I started with, you probably could solve this without doing the math that I'm going to throw at you. But when it gets more complicated, a more complicated network that's not necessarily sidewalks, the process that we go through could solve those as well. So that's usually the case in all the math that we teach in high school. So that's what we say there. Here is the section headings. 6-2 Day 2, Spanning Trees, and Kruskal's Algorithm. Those on YouTube, if I'm saying that name wrong, leave me alone. Okay, and then I'll zoom this back, and I want you to read this but not write it, because again, it's another directed reading, like I said in the previous video that got killed. Okay, when you get this in college, you'd be expected to read the book yourself and figure it out, and then maybe the professor will do a couple examples in class or something. It'd be more complicated, but so you better start figuring that out if things aren't going so well. You could always read the book. Okay, and the key word as you're reading this is seeking efficiency in a network. Okay? And I guess that last example, the sidewalks, is a sidewalk network. And I didn't really tell you what we're going to try to do. We're going to try to save the kids from frostbite here we go. Putting ADD. What was I saying? By putting covered walkways to help the kids or young adults to go from one building to the next. But that costs what? Money. All right, now we'll talk about that later. So we want to seek efficiency, avoid redundancies, and somehow get a connection between all the buildings so a student has a choice to use only a covered walkway to get from any building to another building. Okay, so here's a spanning tree. You actually did this yesterday when you got rid of redundancies so that there were no circuits. It's called a spanning tree, or just a tree. So it's a subgraph. Again, what's a subgraph? A graph taken from an original graph, maybe eliminating some things here and there. We have a tree definitely there. We have not a tree because we have a circuit with that green part. Now, that's a circuit in the subgraph. This whole graph is not a circuit, though. It is, thanks for coming. It is a path, though, right? An Euler path, for sure. Because what's the degree of that, everybody? What's the degree of that? There are students here. There's just one line coming from that. So what's the degree? Yeah, I know. You're still alone. Holy crap. Okay, she can't answer. What's the degree of this? Oh, my goodness. 2. What's the degree of this, and this? All 2s. But what's the degree of this one? 3. So I have 2 odd, and the rest are evens. I have 2 odd. So this is an Euler what? Again, I'm just reviewing for you. We have a quiz tomorrow. It's an Euler path. So where do I have to start? I either have to start at this one or start at this one. If I start at this one, I have to end at this one. If I start at this one, it's simple. Boom, 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 boom. Euler path, every edge is used once. But I don't end where I started, so it's not a circuit. Or boom, 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 boom. If I started over here, it doesn't work. All right, that's the whole point of we did that with the bridge problem. Anyway, blabbering on as you write the notes. Okay, And then I'm just going to reveal, like, how do I remove edges to obtain a tree? All right. So, this is not a tree because we have a bunch of individual whats. Look at that front of that cube. Looks like a cube, doesn't it? It's called a what in this subgraph. Starts with a C, circuit. Okay, so I have a circuit there. So what I could do is remove some edges and then end up with a drawing like such as this, let's say. Now what I did is I removed edges to obtain a tree. Therefore, I have no more circuits in that. So remove the edges so all the circuits are gone, but make sure all of the vertices are in the connection somewhere. So what we're saying is we can do this, but then after I do that, can I, whoops, I hit two at once there. Can I do that, yes or no? No, because what I've did is I've excluded a vertex still being connected to some other vertex, so there is some sort of path to get to that one. So I can't do that last removal. And you did that yesterday. And answers may what? Vary. Okay? So there's another possibility, and there's another one, and so on and so on and so forth. So, what's a minimal spanning tree? We have weights now. All right, that last example I started with that we're going to end with, it's a tree with weights where the edges have numbers on them that mean something. So the next thing I'm going to show you, I'm going to pretend the numbers mean money. We'll just say flat out this means money. And I want to be able to get the cheapest way I could visit every vertex, let's say, or every vertex is connected. So that's what a minimal spanning tree is when we have an overall graph. It's a subgraph where I follow this little pattern of creating the tree. Okay, so if this was a book assignment, which we're smushing everything together, I gave you the worksheet that you should have picked up when you walked in. Some did, some didn't, whatever. But if it was a book assignment, what you should do is take the drawing and draw it, and then right next to the drawing, only do the vertices. Then as you make the selections that step 2 and step 3 say, you draw those in the blank vertices to start filling in the edges. All right, so, and actually your last question on the packet, the drawing is given for you, so all I have to do is draw the vertices and then make the connections. But I'm going to use a highlighter. It works really nice with a highlighter when the drawing's there. So if you actually did the full drawing and then just the vertices, use a highlighter on the drawing and then start transferring those edges over. So what we want is the path that has the cheapest path, I guess, for the example I'm going to show you, that still has all the vertices connected, and it is a tree. That would be the best and most perfect thing. And then the whole idea of acceptable edges, they go through this in the book real good. What's an acceptable edge to use in each step? Basically, an acceptable edge, very easy for me to say, is no circuit is created or no redundancies. They told me last hour that this was spelled right. Does that look right? Redundancies? Yeah. Like dances? Okay. So, again, like most things, when you see the words, they don't make a lot of sense. If you were to have a book assignment, and the drawing in the book was what I have on the left, you might want to draw it instead of marking up your book. And then to the right of that, you draw the vertices, blank, with no edges. Then when you look at this, I just realized 5th hour, this spells turkey. Anyone see that? It just popped in my head with an L in the middle. I don't know. Okay, great. There are people in here. All right. So it cost me $1 to go from E to K. It's a place. K to R, it cost me $2. R to L, it cost me $2. Oh man, T to U, it cost me $8 if I go directly from T to U. I know. Special route. So, what we do is we try to find the tree that has the lowest amount of numbers. So of course, my first selection is select the edge with the smallest weight. Who has the smallest weight? E to K. So I highlight that and I draw that over here and I put my 1 there. So I've connected E to K. That's the cheapest to get from E to K, or that's the cheapest of all of them. Then, what's the next cheapest? Or is there another one? There's another one. So what's my next cheapest? 2. Now, you don't necessarily have to pick this one. I just screwed up. You could select that one next. This is a legal maneuver. I don't know why I changed the red. I'm just leaving it. I don't have the time for this. Okay, but of course you could have also choose you this one. Have I made a circuit? Yes or no? No, so I'm fine. But the reason I did that in that order is it doesn't matter. You don't have to keep, I'm not stuck with, I have to use 7 now because I must keep these connected. No, that's not how it works. The next thing is, the next legal move that doesn't create a circuit, that's the next smallest number. What's the next smallest number on this sheet? 3. Now, should I even do that 3? Yes or no? No. Why? What is that? Circuit plus, no. Actually, L, you can get from E to L as well, but you just have to go through that path. So I have E connected to L through 2 other points. That's another reason why you wouldn't do that. But can I do this? Yeah. So that's another one. We're going to put the number on there. Why is it in red? Okay, what's the next smallest number? I can't do that 3. What's the next smallest number? 4. But should I color in 4? No, because U can already get to L anyway through R. That's the whole point of this. Then you'll see why it makes sense with the sidewalk question. Plus, it also makes a circuit. That's the rules. So what's the next number I should highlight? 6. Which one? It doesn't matter. If I do this one, can I do this one as well? Yes, because that incorporates Y. So Y got involved. So I want to be able to visit all of these, all right? In some way, shape, or form, have them all connected. And right now, when I draw this way with the vertices, I can see every vertice has an edge. So therefore, every vertice can be visited, let's say. So now what we do, and by the way, answers will not vary. I just changed the game on that, right? Unless there was like some more ties, or I don't know. I guess there's a couple other things that could have happened if there were more 2s in here. But with this one, there is only one minimal spanning tree for this, because there is only one minimum. There was only one cheapest way to connect all these vertices when I use the money example. So in very few cases, there would be more than one answer. I can't really think of a way. I could think maybe if some of these numbers were equal. If there's like 3 1s, but then, I don't know. If there were 3 1s here, I couldn't do all 3 1s. You get what I'm saying? Like if this is 1, this is 1, and this is 1. I couldn't do all 3 of those 1s. So now someone could have a different answer than someone else. It's about the only way the answers could vary. In most cases, and actually in the test case, great for me, there's only one possible minimal spanning tree that would work. Okay, so now it's time for the Frostbite example. So you can read this in the book. It ends, it ends with this example being solved, and I'll just go ahead and do it for you. No Common Core here. So these buildings are connected with these sidewalks. Okay, now understand, if I'm going to put a covered sidewalk to save the students from frostbite, right? Didn't I already say that? Okay. To build a covered sidewalk, it costs money for the materials. The longer the sidewalk, what? The more expensive. But also, the longer the sidewalk, we might heat these because of frostbite. I mean, if I just have a covered sidewalk, it's still going to be freezing in there. The bigger the area, the more the cost of heating that covered sidewalk. So there's 2 sets of costs here. So this, again, is a very Mickey Mouse problem. You probably look at this and figure out who'd be covered, but through the glory and power of making a graph out of it, it makes it a lot easier. What's that thing down in the bottom? Ooh. Okay, let's zoom in. Okay, and then go ahead and draw that. And just say, frostbite example, we don't want to hurt children. Covered sidewalks. Cost money. Minimal amount of covered sidewalks to save the children. Something along those lines. Buildings are the letters. This is getting kind of lengthy now. Nice call. So I think someone was doing this on their own. You know what doesn't matter? You're still going to end up with the same numbers at the end. They did flip the buildings around. You know, because here's building A, and then here's B, and then look at in this, here's A, and then they put B here. Okay, so it is the right numbers on the sides. They just decided to put the vertices A, B, C, D, E, and then they started doing the graph like you. Remember, all the graphs can be a little different? Yes, Mr. Samuel. All right, and then, yeah, okay, let's just move on. Let's actually do this now. I sense some people are bored. What's the first thing I should choose? What's the first number I should choose? 120 for the love of dog. The smallest number. Because that represents the shortest distance between two of the buildings, which would be the cheapest to build a walkway and also heat on a daily basis. And that's a legal maneuver. What's the next number I should choose? 200. Because now that connects C to A, and that's the second cheapest walkway to build. Choose what? 210. Now I could build a walkway to there, but I still don't have a connection that gets me from C to D or whatever. So what's the last thing I should choose? Kind of giving it away. 220. Now the students, if I build this pathway that connects these all like this on the outer edge, they would at least have an option to get from building D to building A, right? Yeah. Okay, but would it be a long walk? Sure. So now this student has to make a management decision. Do I want to take a chance and freeze to death? Or do I want to stay in the walkway and go here? But I think the administration should have a sign here, walk here at your own risk on both ends. If you get frostbite, we're not liable because we built you a walkway so you could safely get from A to D. Do it at your own risk. Anyway, you go ahead and add those numbers together. And then we could talk about building costs. And then, okay, we've minimized our costs, and yet we built a walkway that every student has an option, at least, to get from one building to the next safely. There's going to be a note check tomorrow.